let's see, we left off last time here looking at the flux of an electric field. We did this a lot in chapter 0, so a lot of this should be similar to what we've seen before with gravitational fields. We're just going to apply it now to electric charges and electric fields in a law called Gauss's law. And we defined this flux as being the sum of the dot product of E and A, where E is our electric field and A is the area. The area vector will always point perpendicular to the surface. So for example, here where I have a cylinder, the area vector always points perpendicular to the surface, like this. Area vectors in those directions. And that's because we just define our area vector in that way, that it always points perpendicular to the surface. And then our electric field, well, our electric field is what it is. In this case, our electric field runs left to right. And then, so we took the dot product of E dot dA for each of these surfaces. That is the curved surface and then the two end surfaces. Now remember, the dot product, E dot dA, we had this last semester, but our dot product of two vectors is a scalar product, meaning the result is a scalar quantity, and it's equal to the magnitude of the first vector times the magnitude of the second vector times cosine theta. I reminded you that our work, we used that to define our work because we wanted those two vectors that were in the same direction. And that cosine theta takes one component of one vector that's in the same direction as the other vector. So that's what the dot product does. I think we won't see the dot product again. We'll see the cross product again, but not the dot product after this chapter. So anyway, if I have two perpendicular vectors, the dot product is going to be 0. So if I have two vectors like this, because the angle between them is 90 degrees, the dot product will be 0, because cosine of 90 is 0. If they're in the same direction, then it'll be just the magnitude of the two vectors multiplied. So here, where our two vectors are 90 degrees, E dot dA is 0, and so the integral of E dot dA is 0. Here, where the two vectors are in the same direction, E dot dA is just E times dA, because they're in the same direction. The cosine and the angle between that is equal to 1, so that cosine theta, cosine of 0 is 1, and we just get E times the area of that surface. And then over here, where the electric field's to the right, the area is to the left, that's a 180 degree angle difference. And so that dot product is going to be negative E times the area when I take that interval. Okay? So that's just all really just finding the flux. The flux is that sum or the integral of E dot dA. And then once we have these three surfaces, we just add them up, and we found that the total flux in this case is equal to 0, because we had 0 flux here, so our vectors are perpendicular. We had a negative EA and we had a positive EA, and we just add all those up and gives us 0 total flux through the surface. Now what we'll see later, what that means is that the total charge within that surface is equal to 0, and that's really the crux of Gauss's law, is that by measuring the total flux, you can determine the total charge within the surface. And so what we see here is that inside the cylinder, there is 0 charge. Sort of know that with the electric field lines, because if there was charge here, the electric field lines would not go straight through. They would be conformed to those charges in some way. All right, let's do an example. So let's say that we have this Gaussian cube, and there's my electric field, which is 3.0x times I times 4.0 times j, and I want to know what is the flux through the right, through the left, and the top faces. So let me draw this. I wasn't able to put the figure in, but let me just draw what the cube looks like. I have my x and my y and my z axes. And my cube here is going to go from x equal 1, so this is x equal 1, to x equal 3. So it has a bottom that goes from x equal to 1 to x equal to 3. This is the bottom part of my cube. And then it goes up. And it goes across like this. So there's my cube. My cube sits in a place that goes from x equal 1 to x equal to 3, and then it's going to go from y equals 0 up to what? If this is truly a cube, what's it going to go up to? Not 3, but it's going to go up to 2, right? Because it has faces that are 2 meters on side. So this is a cube, 2 meters on side. I know it's 2 meters on side because of this distance is 2 meters, and so this distance also must be 2 meters. So it goes up to y equal 2, and it also goes out to z equal 2. Remember our three-dimensional coordinate system, in case you've forgotten since last year. This is positive x, this is positive y, and this is positive z. You might see different renditions of that, but we use a right-handed coordinate system, and I'll use that. Sometimes you might see the z and the y switch. They just rotate the coordinate system. That's okay.
How do you know that the cube goes from x is 1 to x is 3?
I just told you that.
Oh, so it's not the problem?
It is, yeah. I just couldn't draw the figure very well to include it.
Well, if you put it in the problem like that, you would know.
I would give it to you. I would give you the figure.
Oh.
All right. Alrighty. So that's our cube. This is our electric field. And I want to know what is the flux through the right, the left, and the top faces. That is through the face on this side, that's the left face, the face on the right side, and then the face on the top side. I have this cube. I want to know the flux coming through this side, and this side. We'll return to this problem later, and we'll actually figure out what is the total flux through the cube, given this electric field, and then from that we'll determine what is the charge inside of the cube. But for now, I just want to know the flux through the right face, the left face, and the top face. Again, this is the top face right here. This is the, that's top. This is the right face. And then this side right here is the left face. I just want to know what is the flux through each of those faces. All right, first let's do the right face. Very good. You probably have something like this on the next exam where I give you a Gaussian surface, something similar to this. A regular surface, something that has a very regular area that you'll know, like a cube or a cylinder or something like that. And I'll give you an electric field, and you'll have to figure out what is the total flux through that. Okay? So make sure that you can get this. We've had questions similar to this before, but it's a little more complicated now. All right. So let's first consider the right face. First of all, I want to define my area vector. That is dA. And dA for the right face, my area vector, is going to look like this. Remember, my area vector is always perpendicular to the surface, and it's always pointing away from the surface. Right. So my area vector, if I define this in vector notation, is going to be positive dA in the I direction. These two are equivalent because here I'm expressing it as a vector, and here it's like I'm parsing out that vector information. It's in the positive I direction that has a magnitude dA. Okay? Now I want to write out my expression for the flux. My flux is equal to the integral of E dot dA. I know what E is. E is given up here in vector notation, and dA I just defined as being perpendicular to the surface and away from the surface. And that's going to be the integral of 3xi plus 4j dotted with dA, which is in the I direction. Now, before we can do the integral, we want to do the dot product first. So I can do this dot product. I'm going to have two terms. I'll go ahead and write it out on this one, but I won't write it out on the next ones. It's going to look like this. I'll have 3x dA I dot I plus 4 dA J dot I. All right. I want to know the integral of that. Now, you could expand this integral and say the integral of this plus the integral of this. Right? And we would do that, except we know that one of these terms goes to 0. Let's return to our dot products. Remember, with our dot products, we knew that I dot I, that's equal to 1. Because I and I both have magnitudes of 1. I and I are in the same direction. So I cosine of 0 is going to equal 1. 1 times the cosine of 0 is 1. I dot j, on the other hand, is going to be 1, the magnitude of I, times 1, the magnitude of j, times the cosine of the angle between them, which is 90 degrees, so that's equal to 0. I dot I is equal to 1, I dot j is equal to 0. The same is true that j dot j is equal to 1, j dot I is equal to 0 for the same reason. And then likewise, k dot k is equal to 1, I dot k is equal to 0, j dot k is equal to 0. So basically, with dot product, anytime you have two similar vectors, I with I, j with j, k with k, those are all going to equal to 1. If I have two opposite vectors, I dotted with negative I, that's going to be negative 1. Okay? Because the angle between them is 180. Anytime I have two perpendicular vectors, like I and j, j and k and I, those are all orthogonal vectors. Orthogonal meaning perpendicular at 90 degrees to, then those dot products are going to be equal to 0. Okay? All right. So here, I lose one of these terms. I lose this one because it goes to 0, and so I'm just not even going to write that term at all. So this simplifies to the integral of 3x dA. For this face, for the right face, this is a pretty simple integral because x does not change. For the right face, x is equal to, well, what is x equal to for the right face? X is equal to 3. For this face, x is always equal to 3. It doesn't change no matter over that area. As I move around this area and do this integral, my x remains constant, and so it's always equal to 3. So it's a pretty simple integral for that reason. X is equal to 3, and so I can take that out. X 3 dA. And so the area, this is actually going to be 3x, the integral of dA, which is going to be 3x times just the area of the right face. Okay, so that's going to be 3 times the area of that face. It's a 2 by 2 by 2 cube, so that's going to be 4 square meters. So that's 9 times 4 are 36. The units for our flux are going to be Newton meter squared per Coulomb. It's electric field times area, right? So our electric field here is in newtons per Coulomb. This is our area, meters squared. Now we can do the same for the top face and the left face. I'll erase this right here. For the, let's do the left face next. We go through the same procedure. Our area vector, we first define it. It's going to equal to negative dA times I. because our area vector goes perpendicular to the left face, which is in the negative I direction. So that's why we have the negative, that's why we have the I, because it's perpendicular to that left face, and it's going to be pointing in the negative x direction or the negative I direction. And then we do the same thing. We say that our flux is equal to the integral of E dot dA, which is going to be, this is our flux on the left face, it's going to be 3xi plus 4j times negative dAi, or dotted with, excuse me, not times, dotted with negative dAi. In a way that we did similarly before, I can just leave out that j term, and I get this is the integral of negative 3x dA, because when I do this dot product, doing the dot product before the integral, the dot product 4j, or negative 4 dA j dot I is equal to 0. Remember your dot product, okay? Anytime you have two perpendicular vectors, their dot product is going to be 0, based on our definition of what the dot product is. Okay? Then we can, we know that x equals 1 for the left face, just because of where the left face is. And so this becomes negative 3 times the integral of dA, which is going to be negative 3 times 4. So our flux here is going to be negative 12 Newton per Coulomb meter squared. Let me step back through that. It's the same steps. First, I define my area vector. My area vector is perpendicular to the surface. Since I'm doing the left surface, it's going to be in the negative x direction, so it's negative dAi. Then I go back to my definition of flux, which is the integral of E dot dA. This is E, it's given in the problem. This is our new defined area vector. Here I recognize that the j dot I term goes away, so I just leave out that j dot I term, and I just go with my I dot I term, which gives me negative 3x dA. Then here I recognize that x is constant. Because of my surface, x doesn't change over that surface, so x is equal to 1, and then I do the integral. But it's a simple integral, I'm just doing the area of the face. It's just a constant. All right, and now we can do the top face. That left face was basically the same as the right face. The top face is a little bit different because of our dot product. Notice with the top face, our area vector is going to be positive dA in the j direction, because our area vector goes perpendicular to the surface in a positive y direction. So the flux on the top is going to be the integral of 3xi plus 4j dotted with dA in the j direction. In this case, I only include this dot product because the I dot j goes away. It becomes 0. And so this is the integral of 4 dA, which is 4 times the area, which is 4 times 4, which is 16. Newtons per Coulomb meter squared. Electric field times area. Then if we want to know the total flux, I just add up those three values. I say this plus this plus this. That's 36 plus 4, which is 40. The total flux is 40 Newton meter squared per Coulomb. Just add up those three. Now that's not the total flux through the cube. We'll come back to this problem a little bit later after we see Gauss's law, and we'll calculate the flux for the other three phases. It works out largely the same way, and we'll figure out the total flux for the whole cube. But for those three phases, that's what the flux is. The flux through those three phases is 40 Newtons per Coulomb meter squared. All right, that brings us to Gauss's law, and this is really where Gauss's law becomes useful and where you have to figure out this flux, because if you know the flux through a closed surface, then you can find the charge in that surface. Y'all with me on this? Sort of throwing a lot of stuff that we've seen, or not a lot of stuff, but the dot product we saw last semester. Don't be thrown off with the calculus. It's really not that complicated calculus. You really just recognize that you're not doing really any, trig or any kind of funky integrals, because we're looking at constant values. But embedded in here, we are doing these intervals. They're just very, very simple intervals. All right, let's look at Gauss's law. Gauss's law is pretty simple. We had Gauss's law for gravitational fields, and if we found the flux due to our gravitational fields, then we can know what mass was enclosed in that Gaussian surface, that imaginary surface, that closed surface. You could determine the amount of mass that was inside of it by looking at the gravitational flux that came from that surface, the total flux. You can do a similar thing for electric fields. In electric fields, the flux is equal to the enclosed charge divided by the permittivity of free space. So here, epsilon naught, this is the permittivity of free space. What it's called, it has a value equal to 8.85 times 10 to the minus 12. Let's see, the units are seconds to the fourth a squared over meters cubed kilograms. This is also often expressed, and in fact it sort of goes back to the definition of this epsilon naught, which we won't get to until the second part of chapter 2, in farads per meter, based on the capacitance of a capacitor. But for now, this is the value for epsilon naught, and it's on your equation sheet. Don't bother memorizing it, but just know that it's there. Like I said, as usual, you want to print out that equation sheet and just know what's on it. All right, so this is Gauss's law. This is also on your equation sheet. So if I know the flux that's coming from a surface, then I can find the enclosed charge. Oh, by the way, excuse me, this is also related, sort of as a little thought bubble. This is also related to our Coulomb's constant, which is 1 over 4 pi epsilon naught. So let's say that I have 3 surfaces here, and if I want to know the total charge that's within the surfaces, I have this first surface right here. I'll call this S1. This is S2, and I'll call this S3. You know what charge is in here, but let's say that you didn't know what charges were inside these surfaces. Then we can look at the flux lines. We can measure the electric field in and around these surfaces and figure out then what is the total charge within each surface. So here with this surface, would I have a positive, negative, or 0 flux through this surface? Positive, negative, or 0 flux through the surface. Remember the flux. Our flux is defined as the integral of E dot dA. So if I have a positive flux, the net electric field will be emanating outward from the surface. If I have 0 flux, then I'll have the same amount of flux going in as I have coming out. And if I have a negative flux, the overall field lines will be going into the surface. So they'll be opposite the area vector. Let me say that again. This is our flux definition. E dot dA is positive when the electric field is in the same direction as the area vector. So our flux is positive when our electric field is emanating outward, perpendicular to the area, in the same direction rather as the area vector. This is positive when these two are in the same direction, which is going out. It's 0 when I have equal amounts going in and coming out, because positives and negatives add up to 0. And it's negative when the electric field and the area vector are in opposite directions. So for example, if I had a spherical Gaussian surface like this, and I have electric field lines going in like that, that would be a negative flux. If they were emanating outward, it would be a positive flux. If I had equal numbers going in and out, it would be zero flux. So what about this green surface right here? Does this have a positive, negative, or zero flux? This has a positive flux because the field lines are coming out. You have more field lines coming out than going in. What about this one, S3? Negative flux. And this one, S2, zero flux. So you can see this one is zero flux, by the way, because I have, in this figure, I have two field lines coming in, I have two field lines going out. That's a little more complicated than that because you can draw as many field lines as you want. But in this particular case, I know that my net flux here will be zero. I know that because there's no charge inside of the surface, and by Gauss's law, if there's no charge, then the net flux has to be zero. Okay? So the net flux, if Q is positive, the enclosed charge is greater than zero, then the flux is greater than zero. And that's how it is on surface 1. If Q enclosed is less than zero, then the net flux is less than zero, and that's how we have on S3. And if Q enclosed equals zero, then the flux is equal to zero, and that's how we have on S2. All right, we'll do another example next time. I have a few clicker questions. Let's do those. Consider this Gaussian surface. Now this Gaussian surface, this box, does this box contain a net positive charge, no net charge, a net negative charge, positive charge, or a negative charge? These are in effect. If you want to follow along. Does this box contain a net positive, a net no net charge, a net negative, a positive charge, or a negative charge? Which is it? What you want to do is ask, what does the flux do? If my flux is positive, then it has a positive charge. If my net flux is negative, it has a negative charge. If my net flux is zero, it has no charge at all. So we'll look at the electric field vectors, which are those red vectors, and ask, what is the net flux? Positive, negative, or zero? Let your 1, 2, 3, 4, 5 be A, B, C, D, E. All right, I'll stop at 115. Ask your neighbor if you're not sure. Okay, y'all are sort of all over the board here. Let's look at our electric field and the flux that originates from it. So due to this electric field vector, I'm going to have a negative flux because it's opposite the direction of the area vector. Remember, the area vector always goes perpendicular to the surface and away from the surface. So that has a negative electric field, or negative flux rather. This one has a positive flux. This one has a negative flux. This one, what does this one right here have? That one has a negative flux, positive flux, negative flux. So, some of these will cancel out, like this one cancels with this one cancels with this one, and I'm left with a net negative flux. And because I have a negative flux, that means I have to have a net negative charge. So C is the right answer here. You want to figure out what is my net flux. My net flux, which is the dot product of E dot A for each vector. if the vector goes into the surface, it has a negative flux. If it's coming out of the surface, it's going to have a positive flux. These are all perpendicular to the surface too, and the electric field vectors are the same length, so they're each going to produce the same magnitude of the flux. The total electric flux through this box is what? The box, I'm not sure if you can see it on the board, it should be in your book, but the box looks like this. It has the area, looks like that. This is a cube, it's like a cross-section of a cube, but it is a 1 by 1 by 1 meter box. All right, just a few more seconds. I'll stop at, say, 105, 105, just guess if you're not sure. We're sort of all over the board right now. Okay, so here what we want to do is we want to find E dot dA. Remember, this is a cube, right? So this thing has a 1 by 1 face here, and it comes out. It's a three-dimensional shape. Now, some of these parts of the cube will not have any flux at all. So if I imagine this cube coming out, here's the two sides, here's the front, the back is here, and then I have the top and the bottom. Which sides of that cube will have flux? There are only two sides of the cube that will have flux. Only the top and the bottom will have flux. The sides won't have any flux because there's no electric field vectors going through them. The front and the back won't have any flux because there's no electric field. The electric field would have to be going in this direction in order for the front and the back to have an electric field. It's only the top and the bottom that have an electric field. That electric field has a magnitude of 1 Newton per Coulomb in both cases. So remember, I can say the integral of E dot dA. Only going to do the top and the bottom because those are the only ones that have my flux, that have an electric field. So the flux for the top will be the electric field, which is 1 Newton per Coulomb, times the area, which is 1 meter squared. Right? It's a 1 by 1 by 1 meter box. This is positive because the electric field is in the same direction as my area vector. My area vector is in that direction. The electric field is in the same direction for the top. So this is equal to 1 Newton per Coulomb meter squared. Similarly, in the bottom, now some of you might have said that the bottom was negative, but it's not. The flux through the bottom is positive. It's positive because my area vector is in this direction, and my electric field is also in that direction. And so the flux here, E dot dA, is going to look exactly like this. Actually, it'll look a little bit different. The flux on the bottom is going to be negative 1 Newton per Coulomb times negative dA because it's in the negative x direction. And so that makes it positive, the integral of that. So it's going to be 1 Newton per Coulomb meter squared. And then if I add up the total flux, it's going to be 2. You could envision a case in this same question where it's 0 or where it's something else. How could I make the flux through this box 0? Right, if I had all the electric field vectors going in this direction, if I did that, then it would change this, making it negative. And then 1 plus negative 1 is 0. Okie dokie? I know this is sort of new, like you've probably never seen fluxes or fields, except, we did it back in chapter 0. But we're going to see it again on this next test. And you'll have questions like this, like the cube question that we did. So there's also homework questions. let me see what the next question is. We might do this. Yeah, let's do this one. This will be our last one. These are two-dimensional cross-sections of spheres. So that have charges in them. This has plus Q, this has plus 2Q, and this has plus Q in it. This is a sphere, this is actually a cube. They all have a radius or a side R. And then these are other cubes with Q and plus 2Q, but have a radius 2R. I want you to rank the fluxes, A through E, in their proper order, from largest to smallest. Is that right? Yeah, largest to smallest. Which has the largest flux, which has the smallest flux, and then rank them in that order. While you're doing that, I'm going to go ahead and hand out your exams. We'll come back to this. I'm just going to call out your names. Show them come up, and then I'll give the answer to this. But go ahead and start thinking about it, and just tell them when I call your name. So Desiree, Chrissy, Taylor, Christine, Eric, Brennan, James, Brandon, Domain, Chris, Brandon, Kiat, Stephen, Brittany, Casey. Brennan's not here, right, Brennan? Chris. Casey? All right, Brooke, Cody, Lazarus, Claire, Ainsley, Devin, Ashley. Steve, Logan, Kayla, Kylie, Megan, Taylor, May, everybody else. All right, folks. I do have a couple. I have a couple derivations here. So if you didn't get your derivation and you want it, I know Chris have yours. Just come see me afterwards. I'll give it to you. All right. Let's finish this up. I'm going to stop this at 3:22. Let's see. See? No, that's not right. Look, you can return back to Gauss's law. Gauss's law just saying that the flux is equal to Q enclosed over epsilon naught. And so the flux is directly proportional to the enclosed charge, irregardless of your Gaussian surface. So I can tell you that this one, and this one are all going to have the same flux. Doesn't matter about the Gaussian surface. That all comes out in the wash. No matter the size of your Gaussian surface or the shape of your Gaussian surface, the total flux is going to be directly proportional to the charge. This one, and this one all have the same flux. This one and this one will also have the same flux, but twice the amount of flux. They're all going to be positive flux. B and D will be bigger. I'm sorry, not B and D. B and E will be bigger. So B is the right answer here. Don't worry, we still have another day in this chapter, at least a day, on Monday. And so spend the weekend, maybe look through the homework. There's some homework questions that are very similar to the ones we worked today. Look at those. You can think about the rest of these questions if you like. If you have questions about your exam, I'm Stevie. Don't fret it. Get to it all the way in life. Still a lot of opportunity. We still have 2 more tests before the drop day. 4 more tests overall. We're good to go, okay? See y'all later. Have a great day.